Hi guys, welcome to my YouTube channel. My name is Ndlovile Bohang, and today we're going to be learning about equilibrium of a particle in mechanical technology. And don't forget to like and subscribe. So a particle is said to be in equilibrium when the vector sum of all forces acting on it is 0. Okay, by that we mean that there's no acceleration, and the whole sum of their forces is equal to 0. Okay, so it means that there is no unbalanced force acting on that particle. There's no resultant force on that particle. Okay, so we have rules which we have to abide on when we're on this topic. Rules number 1: draw a clear body diagram. We have to have a very much clear diagram to allocate the forces that we have on that certain problem. Okay, number 2, we have to choose convenient coordinates, axis. You understand, the x-axis and the y-axis. Okay, and number 3, we have to resolve all forces into component. We should have the y and the x component. Okay, and then number 4, we should apply the equilibrium condition, which says sum of vertical forces is equals to 0 and the sum of the horizontal forces is equals to 0. Okay, and then number 5, we're going to be resulting into solving the resulting Smeltenius equations. Okay, so here there are questions which we're gonna be doing while based on this topic. Okay, so we have the first sum, which is this one. In order to solve that sum, we need to draw a free body diagram which has all the components, right? And then we're gonna solve, and then we're required to do what? To find all the forces in each supporting the cable, right? We're given that the crate has a weight of 500 newtons, and we have to determine the force in each supporting cable. Okay, right, so let's do it. Okay, so number 1, you know that we have to abide by the rules that I have mentioned before. Oh, sorry, my whiteboard is acting up, but we have to abide by the rules that I have mentioned before, which are this rule, which we have rule number 1, which is to draw the free body diagram of this thing, and then number 2, we have to find the what? We have to choose the convenient coordinate, and we have number 3, we have to resolve all forces into components, right? And then we have number 4, which is very important, whereby we have to apply that the sum of f of x is equals to 0. Oh, sorry, let me fix this. Okay, all right. Okay, right, so we know that the sum of all the forces is equals to 0. F of x, f of y, or even f of z if we have f of z. Okay, right? If ever we're given f of z, we should always know that the sum of f of x is equals to 0. The sum of F of y is also zero. Okay, right. So, and then there's a point where we have to solve this equation simultaneously, right? And I will show you that too. Okay, so as you know that we have said that the sum of forces acting horizontally are equals to 0, and the sum of forces acting vertically are equals to 0 when added all together. Okay, so let's delve deep into solving the question. Okay, right. So we have to remember rule number 1, which is to draw the free body diagram, right? All right, let me just, okay. So we have to draw the free body diagram representing all the forces acting on this equation. Okay, we would need a ruler for that. Okay, let's put it here and then let's turn it into our wanted. Okay, right, let's draw. Okay, so we're first gonna draw. We have to break down the whole problem. We have to break it down into a simpler one. Okay, all right, let's do it. Okay, and then let's turn our ruler to how we want it to be. Okay, all right. Okay, all right, there. No, it's not straight. Yes, perfect. So the line going down. All right, so this is what we have so far. Oh, it's so long. The line going down is so long. Okay, let's remove this part. Okay, yep, yes, we can work with that. Okay, so we are working to solve our first problem, right? We should always know that we have components, right? And then the first rule was to draw a body diagram. So right now we're going to break down the whole structure before we go to the body diagram, the free body diagram, meant to say. Okay, so this is what we have. We have a force going this side and another force going this side. Okay, right, let me fix this force. It looks like a snake. Okay, let's fix. Oh, I'm ruining everything right now. Okay, I'm gonna fix it. Let's fix. So we have this one and this one and this one. Okay, we have forces acting in different directions, which we can actually call them force T1 and force T2. T1. As you always know that every force which is a cable is always tension, which includes a rope or cable. It's tension. And here we're told that determine the force in each supporting cable, which means we're on the right track. Okay, let's proceed. So as we know that in equilibrium of a particle we don't have acceleration, we're going to be dealing with the SOHCAHTOA. Let me fix this. We are going to be dealing with the SOHCAHTOA. Okay, right. Okay. Okay, we're gonna be dealing with the SOHCAHTOA. So we know that SOHCAHTOA is it's sine over hypotenuse. Ka, it's cos, which is normal. Sine is opposite over hypotenuse, and then cos is adjacent over hypotenuse, and then tan is opposite over adjacent. Okay, so we are going to be, let me increase the brightness here. Right, so we are going to be solving for the cables T1 and T2. So here we have a cable, an extra cable, which is carrying the weight. Oh, sorry. Which is carrying the weight. Let me use another color. Okay, red, it's good. Okay, there's the crate. Okay, and then we have another force, right, another cable right here, other than there's two cables. All right, so in this one we're told that we have been given that it is 30 degrees. Okay, so in this one we're given this type of shape, a smaller triangle, but we know that if it's a small triangle is here, we're gonna use this SOHCAHTOA to solve for the angle, but now we're not solving for the angle. So okay, the length of this is gonna be, the hypotenuse is, okay, let's just draw this thing first. Okay, comes and then, okay, right, then we have a 5 here, 5, and then there's a 3, and there's a 4. Right, okay, so here those things are held by some things here. Okay, let's just do this. This is named B, this is named A. Oh no, it's not named A, it's actually named C. Okay, let's remove this. Yeah, okay, I managed to remove half of it because I cannot remove everything. It's like I'm erasing the whole thing. Okay, here it's C, and here it's A. At the starting point it's A, and then we have D here. So, and we're gonna have T3, right? Okay, so as much as we have T1, T2, and T3, and we know that we're gonna be using the socket tool. Now we know that we can start on our free body diagram. Okay, so this is how we're gonna draw our free body diagram. Okay, let's label T1, T2, T3 first before we go to the free body diagram. All right. Okay, so T1 is gonna be equal to AB. T2 is gonna be equals to AC, right? T3, which is gonna be AD, which we're actually not looking for, but it's gonna be useful somewhere. Okay, right, so now is the time to apply by the rules. Okay, let's remove this so that we can draw our free body diagram. Okay, let's just remove everything. You're not gonna remove those so that we can refer from, right? Okay, let's draw a free body diagram. We're gonna need our ruler as usual. Okay, let's go down. Okay, let's rotate it so that we can draw. Okay, right here. Okay, let's draw the second line, which is gonna be here. Okay, all right, so this is our Cartesian plane, but we're actually drawing a free body diagram, and we always know that the object in the free body diagram is always represented by a dot, right? So we're gonna put a dot here so that it shows that this is a free body diagram. So these are forces. These are the forces. And we should know that the force, we already have weight, which you're gonna name weight AD, because it is holding it is. But we're gonna have the weight because we have the tension, and then we're gonna have the weight over again. So right here we're gonna have a BY and a CY, CX and a BX, because we have two forces acting like this, and then the vertical component, as we have 2 points, which is C and B. The vertical component, they should be CY and BY, and then we're gonna have a BX and CX, right? Okay, I hope you understand. So let's draw another force here, and okay, cool. And then let's draw the gravitational force. but we are not gonna need the gravitational force, but already it is going down, so we have the weight. So we're gonna name this one A. Oh, let me fix this. My pen is acting up today, but we're gonna figure it out because we are here to learn, right? Okay, so we have A, D, and then we have C, Y, and C, O. Let's fix it. I love fixing. I don't know why it's drawing a lot of lines today, but okay, we're gonna figure it out. We have to work with it, okay? And then we have C, O, X. X, it's X, not Y, it's CX. Okay, we have CX. And then we have BY and BX. Okay, right. And this is how our free body diagram is looking like. And then we have another free body diagram because we have a crate here, and it is holding, it is being held by a rope, right? But then it has what? Weight, because it is pulled down by gravity, as I said before, okay? So we're gonna have the second free body diagram right here. Okay, and let's fix this line too. Okay, so we have AD, which we have included on that free body diagram before, because that is actually needed on that free body diagram. And then we have weight. So this is the trick. We have two body diagrams, but we are actually going to use one. So, and then here we have drawn our free body diagrams. Step 1, rule 1 of solving a equilibrium of a practical question. Okay, let's start solving. So, all right, we're coming to that part, the trickiest part. So, as we know that we have tangent, which is going to help us to find we have SOHCAHTOO. We have two trigonometric ratios which are going to help us to find the angle here, and then we're going to use the tangent, because it is opposite over it is opposite over adjacent. Okay, so we're going to be working with it. Okay, so let's proceed. And then we know that we have trigonometric ratios, as I've said before, that those trigonometric ratios are going to help us in solving this whole problem, right? Okay, we are gonna find the angle, which is, okay, let me bring back that diagram so that you can understand which angle I'm talking about. We already have this angle, so we're gonna find this angle using that small triangle connected here, right? Okay, so trying to find that angle, we're going to use trigonometric ratio, which is tangent. Tangent is opposite over adjacent, which is gonna be the tan theta is equals to up. Okay, let's reduce this. Oh, we're having a hard time working with the pen. Okay, because it's so slippery, let's use this other side. Okay, we have opposite all over adjacent. Okay, right, we have opposite over adjacent, which is gonna be equal to, and then our opposite over adjacent here, it's, this is our opposite and this is our adjacent. Okay, then it's gonna be 3/4, right? Oh, it's so squishy. 3/4. And then we're gonna let turn to the other side so that we can have a tan function, and then we're gonna solve for theta. Okay, so solving for theta, we are going to have tan function of tan with the opposite and adjacent that we have. Okay, right, so we are here so far. Okay, so the answer is gonna be, let's punch our calculator. The answer is gonna be tan 3/4, which is equals to 36,869. We're going to take the three decimal numbers, the three numbers after the comma, which is 36, comma what, 869. Okay, 8, 6, and a 9, which is on degrees. You should never forget the unit of anything. It's on degrees. Forces are in what, newtons, and then this is on what, degrees. Okay, so this is what we're gonna do. We know that T3 is equals to weight, which is equals to 550 newtons, as we are given here. Oh, sorry. This whiteboard keeps on going out, coming in, going out and coming in. Okay, at least our things are not out. Okay, let's work with it. Okay, all right, so we are going to find T1 and T2, which is AB and AC, right? Okay, let's proceed. So here, as we have found, this force here, I mean this angle here, we're going to start solving for the sum of the x intercept. Or component. Okay, right, let's solve for them. Okay, all right, so we're gonna have this. You should indicate that always when you're solving for the sum of f of x, it's given by, it's equals to 0. Always. This is very important. You should always know this. The sum of forces horizontal is equals to 0. Always. Okay, let's move. So we have TA C, because it is, you should always know which force is positive and which one is negative, and then the ones this side are positive, the ones those side are negative. So we're going to minus the B side, minus T A B is equals to 0. Okay, so we are here now. So we know that we're given that the formula, we always know that the formula of calculating the horizontal component is F cos of theta. So we're gonna have T, as we have found the angle here for the forces in C. We know the angle for the force in C. So we're gonna use it to calculate the T, the cos of 36 comma 869 869 minus T cos of fix cos of the cos of, okay, let's go back. The cos of 30, we're given that is T to the cos of 30, and you know that it's, as I've given you that TAD, this is D here, okay, T1 is equals to this, T2 is equals to this, and we won't be needing this. Okay, so here you can write T2, and here you can write T1. Okay, all right, let's proceed. And then you should always indicate that it's equals to 0. Thank you. All right, let's proceed. So here we're gonna have this answer. T1 is negative, so it's gonna go to the other side, which is gonna be T2 cos of 36, comma 869 equated to T1 cos they are bonding. Okay, cos of 30. Okay, let's remove that. Cos of 30. Okay, and then we're gonna divide, because we want T1, we're going to divide by the cos of 30 both sides. This and this will cancel, so we're gonna be left with T1 is equals to T2 oh wait, let's fix this. Okay, oh sorry, it's T1 it's equals to 36, comma 8, 6, 6, 9. Oh, let's remove this. It's gonna be, we left T2 cos. It's gonna be T2 cos 36, comma 8, 6, 9. Oh wait. Alright, let's remove this. Divide by the cos of 30. Hey. The cos of 30. Right, and then this is equation 1. Right, so we have our equation 1 here for the sum of the horizontal forces. This is what we have. Okay, right. So let me remove this. To move it automatically, because we cannot afford to like lose this information. Okay, regardless of everything, let's move. So we're going to calculate the sum of the y, or the vertical components, and then we're gonna have f. Oh, no. Excuse me. We are going to start by saying that the sum of forces which are vertical, the sum of forces which are vertical is equals to 0. You should always know this. No matter what, you should always write it. This will help you in solving all your problems. Okay, thank you. So we're moving. This one is gonna be a little bit longer. Okay, so it's gonna be, because on the horizontal we have the 550, remember? Okay, let's move. So we're gonna have, and it's all positive, all of it is positive except the one going downwards, it's negative. So we're gonna be having it as T1, as you know that it's TB, TAB. It's equal to T1 sine of 30 plus this one, we're adding them together, T2 sine. We're dealing with the horizontals, that's why we're using sine instead of cos. 36, comma, 8, 6, 9. Then we're minusing the weight, which is 5. 50, and equate it to 0. Equate everything into 0. Okay, we're equating everything as 0. Okay, right. It's equals to 0. Okay, so excuse me, from here onwards we're going to take the 550 to the other side. All right, let's do it. Okay, as we want to solve for T1, right? Yes, we are going to solve for T1. So T1 sine 30. Sine of 30 minus T2 it's plus. Actually, we can just let, we can just put in the T1 already. Let's just put in the T1 because we have T1 here. We have it here. So let's just put it in and then we see how where it led us to. T1, it just said that it, no, now we're solving for the forces. T1, it has said that it's equals to T2 cos of 36, comma 8, 6, 6, 9 divide by cos of 30. Then we're gonna put everything inside the bracket so that we can introduce the sign. Multiply by what? Sine of 30. Okay, plus we are not forgetting this T2. So now we have the same numbers. We have numbers which go in pairs, which we can add and subtract. Sine (36) (8, 6, 9) is equals to 550. Okay, so now we are going to solve everything here, right? And then we're gonna have T2 we have to punch everything on the calculator, so it's going to give us 399,999 times 10 to the power, because we're going to be multiplying. This one is going to be divided by 1. Okay, so we're going to multiply like this. So it's going to be, let's do, and then the answer is going to be 399, 9995. I said we take the numbers, the first three numbers over there after the comma, times 10 to the power -3. Okay, divide by the cos of 30 plus, you don't forget this one, right? Plus T2 sine when we come this side, it's like we're dragging this thing away. Sine 36, 869, which will give us the answer of 550. This is very long. I'm sorry, this is very long, so we have to bear with it for a bit because it's longer than I thought. Okay, right, so let's continue. This is how we're gonna be solving this, right? And then we're gonna take out the common factor between the two, and then we are going to get our answer, which is, let's multiply the whole thing. Okay, 399,995 times 10 to the power -3 divided by cos of 30 plus the sine of 36,869, which is gonna give us a 1, let's enlarge here, which is gonna give us 1,066,2, because it can never be, it's equals to 550. And then we're gonna divide both sides by 1,062. Divide this side, 0,62. This and this, they go. T2 is equal to 550 divided by 1,062, which is equals to 517,891 newtons. So we have found T2. So let's go back to T1. T1 is equals to 1,062 You can choose which one you want to use over here, but we have T1, which is equal to T2 cos that, and then T2 we do have, which is gonna be 5, 1, 7, comma 8, 9, 1 cos of 36. Oh, I better that side. Okay, we're gonna fix it. Thank you. Comma 36, comma 8, 6, 9 divide by cos of 30. So one is equals to answer, okay, 517, comma 891 cos of 36, comma 869 divided by cos of 30, which is equals to, okay, okay, the answer is 478, comma 413, 413 newtons. Okay, so we got the answer for the first problem, for the first example. It did take long because we had to, you see, here we applied all the steps which were required to solve here. Okay, we applied all steps required to solve here. Number one, we drew the free body diagram. Number two, we looked for the particular, we chose the convenient coordinates, the x-axis and the y-axis. Okay, number three, we resolved all the components, right? Number four, we solved for the forces simultaneously, and number five, we actually solved everything, right? We did solve. So this is how it's gonna be. The sum of horizontal forces is equals to 0. The sum of vertical forces will be equal to 0. So let's move to the next problem. Let's say that we're going to be moving to our next problem. Let's remove this. Okay. Okay, let's remove everything so that we can move to our next problem. Okay, okay, let's proceed. I'm sorry, It exits and enters all the time. So let's just proceed. Okay, so right now we're gonna be going to problem number 4 because it's a little bit different from the other. Okay, we have problem number 4, this one. Right, it says if the mass of a cylinder C is 40 kg, determine the mass of cylinder A in order to hold the assembly of in the position shown. Okay, so we're going to draw free body diagrams. That's the first step, and we haven't forgotten about our Sokoto. Okay, so let's proceed. The first free body diagram, we should have an idea of what we're working with. So this is how the structure of this thing is. It is like this, going with an angle here, L. Okay, let's fix this. But then you understand that it goes with an angle over there, so let's fix it. Let's start over. We have this node here. It's a circle which is holding this force going with an angle, this force, this going downward, and this one going to the left. Okay, let's fix this one. Okay, so let's redraw it perfectly. It's going like that. Okay, so we have a force here in between, right here. Okay, so this is what we're looking at, and these things are carrying heavy things. There's something here and there's something here. Okay, and then here it's attached to something to hold here, and then even here there's something that is attached to hold this part. Okay, so we're going to draw. Okay, it is labeled B, C. Oh, sorry. Why am I drawing a line? It's labeled B, C, C, A. In most cases we don't need a D, but then okay, that's just okay. And then we have a E, which is a point at the center. Thank you. All right, so we're going to draw free body diagrams, and what we're looking for is what? The mass of A. Okay, let's draw the free body diagrams. I hope you understood here what we're dealing with. Okay, let's not forget our Sokoto. It's all about the Sokoto. Okay, let's draw the free body diagrams. As you know, that's the first rule of solving an equilibrium of particle problem. Okay, let's draw the free body diagram of A. It's gonna be like this, which it doesn't. Okay, let's just draw it. This is A, okay, it's weight, and this is AE. We're gonna name it AE. Okay, then we have our second free body diagram. Which is going to be C, B, and no, this one I don't include. We have the one which has components, I'm sorry. Okay, let's go. It is like this, which has component. It has okay, let's just put in the components for once at once so that we can see what we're working with. Right, thank you. Okay, then it's going down. There's this component, and there's this component, and there's this force. Okay, right, this one is not gonna be long, judging by how it is so straightforward and simple. Okay, let's do it. Okay, so here, as we have separated the components, this is going to be AE, which is the same as weight. Okay, here we have the C component, which is going to be BE, cos of theta, and then we have the BE, sine of theta, and then we have DE. Right, and then we also have this free body diagram. It is actually necessary because we have to draw it knowing very well all the forces are being indicated, right? Okay, we have this force is called weight, and then we have BC. Okay, right, so these are the free body diagrams we're going to be working with, all of them. Right, okay, let's move. So we're going to calculate the sum of forces, right? The sum of forces of Y of vertical forces, meant to say, I'm sorry, I equals to 0. Always remember this, please. Always. We're not gonna work with the horizontal forces because we have nothing with the horizontals. So we know that weight is equals to mass over gravitational force, acceleration. Okay, so this is what's gonna happen. As you know that CB minus W is equals to 0, which is the horizontal, and then we're gonna be BC is equals to 392. Do you understand? Yes. So let's proceed. CB minus W equals to 0. BC, meant to say not CB, BC minus W is equals to 0. That's the sum of the forces in horizontal. And we know that weight is equals to mass multiplied by gravitational acceleration, which is going to be, sorry, which is going to be BC minus W L is equals to 0. Okay, then BC will always be BC minus, gonna have 40 multiplied by multiplied by 9,8, which is equals to 0. So those forces are equal. BC so we already found the BC. It's equal to let's calculate 40 multiplied by 9,8, which will give us 392, if I'm not, yes, let me check if I'm not mistaken. 392. Now it's necessary to include the 1. Okay, 392 over 4, and then we're gonna have 392 4 newtons. Please guys, don't forget the signs. Please don't forget the signs. Signs are very important, extremely important. We should never forget the signs. Okay, let's move. So we are going to calculate AE now. Okay, so we already have the weight of, okay, we're gonna see where we're gonna go with. Okay, we're gonna have the sum of Fy is equals to 0. We should always remember this, please. No matter what, always remember that. Okay, so we're gonna be given BE, the sign of theta, and always know that force is going up they're both equal, right? Okay, let's do it. BE and BC are equal, so we're gonna use that. BE sine of what? 30 minus A E. Okay, it's equals to 0. Right, let's continue. And then we got, as we say that BE is equals to what, and then we're gonna say 3 9 2 comma 4 sine 30 is equals to A. Correct. Okay, so this is the thing. AE is equal to, let's calculate, 392.4 sine of 30, which is going to be 196.2. 196.2. So we are here, sum of forces going up, it's equals to 0. And always don't forget the direction here. Up is positive, always up is positive everywhere. Even if you can say it here that up is positive. Okay, let's go. Okay, so AE minus WA is equals to 0. And I already have an AE, which is 90 or 96.2, which is equals to mg, which is 196.2 is equal to, okay, let's go. Mg is equals to mass over gravitational, and then we're going to m 9.81, and then we divide both sides with 9.81. This and this will cancel, and then we'll be left with m of A is equal to 90 divided by 2, 2 divided by 9,81 is equals to 20. Then what? Okay. Jeez. Okay. So this is the final answer of our number 4. So all in all, the only thing that you have to do is to follow all the rules I provided at the first time. Like, as you can see here, we didn't solve simultaneously because we didn't have to. It was a straightforward question. So, but then if you're required to solve simultaneously, you have to, because it is part of the rules or steps to comply in equilibrium of the particles. Okay, let's recap. Okay, here are questions which you can solve by yourself. It's questions like this ones. Number 1, you should know that you have to do what? Draw a free body diagram, which is gonna be, you have to indicate first which sides you go to and which sides you're not going to. Okay, let's fix here. Okay, here you choose either. No, you don't choose. You have to first, you have to draw a free body diagram based on what you have been given. You understand? So the free body diagram is gonna be like this. And always know that a free body diagram is indicated by a dot. It is not a force or a vector diagram. It is a free body diagram. It is indicated by a dot. Okay, let's put it on our dot there, and then we're gonna have the CX, and then we also have the CY, and then we have the AX and the AY. And then we're going to have the BD. Okay, let's see. C of X C of Y, A of Y. Make sure that your vertical components are equal. The lines are equal. Don't mind mine. It's because I'm not using a ruler. A, X, and then this is what? BD. Okay, and then you should always know that here it is a Cartesian plane. This side will always be the negative side. This side will always be the positive side. No, the upper part is positive, but it is negative here, and then this part is the negative side. You should always keep that in mind when you're working with this. So I hope I have briefed it clearly so that you understand. So let's go back to the rules. We have to go back to the rules and see if we have complied by all the rules. Okay, let's just swing in. Okay, here are the rules. So far we have learned how to draw our free body diagram. We have learned how to choose our convenient coordinates of the x-axis and the y-axis, and then we have known how to resolve all forces into components, which is the sine theta and the cos theta. The vertical is sine theta, the horizontal is cos theta. We know that. Okay, we were able to know that every time this is a reminder, this is a point which I should emphasize so far. All forces here are equal to 0. The sum of all forces should be equal to 0, and then acceleration is equal to 0. It's like you're applying Newton's first law. Yes, just use the mind of knowing that you're applying Newton's first law. This is when, by equilibrium, we know that every time the average is going to be 0, maybe everything has to be equal. Equilibrium, everything has to be the same. Equal should give you an equal number. It is a point, the equilibrium point. Let's show you by a curve. Maybe you have a curve here. The equilibrium point, it is a point whereby everything is going on the same pace. Everything is on the same pace. It is this point from here to here. You go up until here. Everything goes in the same pace. You should always know that. That's the equilibrium. Everything. But then when it comes to chemical mechanics, you should know that every forces, the sum of the forces of the vertical component is equals to 0. The sum of the forces of the horizontal component is equals to 0. In that way, you will be able to calculate and determine all your answers correctly, everything correctly. Thank you. Don't forget to subscribe. And to emphasize deeply, we have to solve simultaneously in order to, not in every question that we have to solve simultaneously. Some we have to solve simultaneously, some we don't have to solve simultaneously. We just need to cooperate with them. We just need to know how to solve that certain question. Sometimes it doesn't require us to solve simultaneously because maybe they will be looking for mass, like question like that example 4 that we did. We were looking for mass. We were not looking for the tension, the forces. We were only looking for mass, not the forces. So when we're looking for the forces, that's when you're going to be simultaneous. But when you're looking for other part of the problem, we don't go simultaneous. We can go simultaneously, but then it's going to be the longer way. So we can go simpler with everything. So thank you. Don't forget to like and subscribe to my page, and sizobonana kulizayo.